This is part 5 in a set of videos I call Basic Training. I'm going to start off by giving you a challenge. It's a very simple challenge. It says, draw a circuit to operate a lamp. Now this may seem like a simple challenge. However, as electronic engineers, I expect a lot from this simple request. And there can be a lot of things to consider. Let's break this down into little steps. Draw a circuit. Well, what do you need for a circuit? Well, we learned that in a circuit you need a source of energy and you need some type of load. So, when you see the statement, draw a circuit, then immediately you should be thinking about these two items, and you must think about how will the energy get from the source to the load. And we also have to think that the energy flows out of a source from a positive point. It goes out and it has to return to another point called a negative point. That's how the energy gets transferred to the load. And this forms a closed loop. Now this closed loop can come in many forms. And it doesn't have to be a simple closed loop like this. It could also be a network where there are crises and crosses. But no matter how complicated the network might be, somewhere energy must begin and then it gets distributed into the network and it must return. Now we will start off with the most fundamental network, and that is a simple series or parallel, depends on how you look at it. Now let's go to the next word, to operate. Usually operate means that something is on or working. It means it has energy. And what are we going to operate? A lamp. Well, most people know what a lamp is. But in this particular example, I'm being very unclear about the lamp. Why? Because I want the student to decide or choose what lamp. In this example, I'm going to choose a lamp or incandescent lamp, and this lamp is rated at 6 volts, 60 milliamps. I got this information from the data sheet, and this is a picture of my lamp. I'm going to copy this picture just so that we can have an idea of what we're looking at or what type of lamp that we're going to work with. Let's go back, see if I have a second chance. Nope, I don't have a chance. Let's try. There we are. There's my lamp. So this is the lamp that I want to operate. Now it's an unusual shape, but regardless of how it looks physically, we still represent the lamp in electronics as a component that gives off light and has two terminals. And from the data sheet, our lamp needs 6 volts of energy. And if you do provide it with 6 volts of energy, we can expect, as mentioned in the data sheet, we can expect around 60 milliamps of current. As a beginning designer, you should be looking for that information at the very beginning. What voltage and what do you expect for the current? So, step number 1's done. We have selected a load and we got the information that we need about the load. Now, when we say operate, generally we want to turn something on or off. And the most common component that we use to turn things on and off are switches. So once again, we're back to the data sheets looking for a proper switch. It so happens that I have a switch available. Now there are many types of switches. There are push button switches, there are rotary switches, and there are slide switches. The switch that I have a data sheet for is a slide switch. While this is loading, I can draw the symbol for a typical switch. Depending on the switch that you choose, it may have 2, 3, 4, or maybe even 5 terminals. In this example here, this switch has 3 terminals. It is a single pole double throw. What that means is that it can move in 2 directions and close 2 different ways. Here is the general information about the switch. This information here basically tells you that if you're using this switch to open and close a circuit that's rated at 120 volts, the maximum current would be 3 amps. If you were to switch this at 28 volts, you can also support 3 amps of DC current. So this switch is well within our range of operation because our circuit will not be switching 28 volts and it most certainly will not have 3 amps of current. So this should be a suitable switch for our design. Now we need an energy source. Now energy source comes in many forms. So you have to decide what energy source you're going to use. Typically batteries come in energy ratings of 1.5 volts, 9 volts, and 12 volts. Now we could use the 9 volt directly, or we can put some 1.5 volts together. If you use 9 volts, then you most certainly will need a resistor in order to reduce the voltage to 6. However, if you put 1.5 volts together in series, then they can add up to the 12 volts. I'm sorry, to the 6 volts that you need. So let's use that design for now. Let's buy 4 1.5 volt batteries and put them together as we showed before to give us the 6 volts that we need for this light bulb. Now let's look at some batteries. Again, every component that you use in electronics come with some kind of data sheet. It may not seem important now, but when you start designing circuits, it becomes very important because you have to be sure that your circuit or your energy source will have enough energy to operate your load. And you can only get that information by reviewing the data sheets. While this is loading, I'll go back to, oh, here we are. Let's look at some batteries. There's the symbol. There is a basic representation of a battery. Notice that it has this internal Ri. This is because all components have some type of internal resistance. One thing that's important, and I referred to this before, when you are dealing with loads, you talk about words like maximum and typical, because this is information about what it needs to operate. It needs something. But when you talk about energy sources, you use words like capacity. And in this case, we're talking about what it can supply. What can it supply? So when you read data sheet on energy sources, you talk about capacity. What can it supply? What is it capable of delivering? Going back to the data sheet for the battery, batteries are usually rated in milliamp hours or amp hours. And what that means, let's look at an example of a battery. Let's say you go and you buy an alkaline battery, like Duracell batteries. It's typically rated as 2,700 milliamp hours. What that means is this. If you operate this bulb, which uses 60 milliamps of current, then using this, it can calculate for you how many hours it will be available for you. Let's put it into the calculator. 2,700 divided by 60 equals to 45 hours. There are 24 hours in a day, so if we turn this circuit on, it will operate for 2 days, or approximately 2 days, at 60 milliamps. But of course, as the battery begins to weaken, then its output will probably begin to decrease because the internal resistance of the battery will begin to increase, and it will not provide the full 6 volts as you expected. But it seems that our circuit now is just about complete. So we have dealt with the load. We've dealt with how we're going to deliver, or how we're going to control the source to the load. Now we just need, how do we actually get the energy from the source to the load? Well, in order to do that, you need something called wire. Now that wire, even wire that you buy, has a rating. I won't discuss that now, but just understand that you cannot use any wire. The wire has to be of a proper type, like copper, or maybe silver or gold. I forgot what the symbol is for silver, but I do remember gold. And sometimes you have other types of metals. But all of this adds to the design process. This switch can be opened or closed to control when the energy will be delivered to the load. So now we have finished our task. We drew a circuit to operate a lamp. Now I'm going to finish the complete labeling of the circuit. This I will call A. I will call this B. And down here I will call this C. I will use this as a reference point. Current will flow through here, through here, through here, and likewise it will also flow through the wire. All of the current has a name. This is the load, or the total current, should be T. This is the lamp current. This is the current that's flowing in the wire. This is the current that's flowing through the switch. And we know from our electrical theory that all these currents will be equal to each other. Then you have something called a source of power. And then you have V switch. And then you have V lamp. And you may not realize this, but you also have V wire. But usually the voltage across the wire and the voltage across the switch are very small, so that the voltage from the energy source will be very, very close to the voltage across the load. So everything here is properly prepared for analysis. and even construction if necessary for testing. This circuit diagram can also be used as a simple form of a wiring diagram if you are good at reading these circuit diagrams. But you can see that this symbol is a lot different than the actual object itself. But at least here you can get started. That's the end of this lesson, part 5 on basic training.